Hello, dear friends, my dear students. In last video, that is in video number 31, we have gone through D to A converters, digital to analog converters. Let us review of last video and then we will review fast for the last video and then go for A to D converters. We have seen this DAC, D to A converters. This is D to A converters. We have gone specifications of D to A converter. These are the specifications which we have seen. Types of DAC, binary weighted DAC and R to R ladder type DAC we have seen. This is the circuit of binary DAC. This is equation and this is the equation of binary DAC. Limitations of binary weighted register type DAC. These limitations we have seen, and then R to R ladder type DAC we have gone through this circuit also. And R to R ladder type DAC we have seen some specifications and some points on this video. The output equation of R to R ladder network and then error in DAC. These errors we have seen. Now we are going to study A to D converters. I am here Lalit Kumar P. Bhaiya, Associate Professor, Electronics and Telecommunication Engineering Department, Bharati College of Engineering and Technology, Durg. Today we will learn about this analog to digital converter. Shortly it is abbreviated as ADC. Let us see. This converts the analog signal into digital data, that is ADC, used in data acquisition system and digital instruments, etc. The use of the A to D converter. It is used in DAS particularly. Here, schematic representation of A to D converter. This is shown here, the A to D converter. This is the start of conversion and this is the end of conversion. This will be provided as a start of conversion signal and this is obtained as the end of conversion signal after the process is finished. Here analog input is applied for which we have to convert it into digital. And here we will get the digital output. That depends upon the number of bit. Here n bit are shown, B0, B1, B2, B3 up to Bn. Depending upon the number of bit, we can consider this A to D converter. Then types of ADC. Counter type ADC, number 1. Number 2 is successive approximation ADC, that is in your syllabus. Particularly, the name is given in the syllabus, successive approximation ADC. Flash or parallel converter type ADC, this is also in your syllabus. Integrated type of ADCs. And single slope and dual slope integrated type of ADCs. So these are the A to D converters from which we will see first the counter type ADC. This is the circuit diagram of counter type ADC. Block diagram you can say, rather than circuit diagram I can say block diagram. Here you can see in counter type ADC, analog input is applied to this comparator. This is non-inverting terminal where we will apply this analog input, and this is inverting terminal connected to the D to A converter output, that is feedback. Here clock signal is there, gate AND gate is used where clock signal is applied and output of the comparator is applied. So output of comparator continuously compared with the clock signal and it will provide the ANDing. This ANDing output will be obtained from the AND gate and this is applied to the counter. Counter will count the pulse according to the analog input and clock pulse, and this output is obtained called as the digital output from LSB to MSB. This is LSB, this is MSB. So you will get the digital output. And if there is a change in the digital output, or according to the bit position, this feedback is given to the comparator. Again, this analog input and comparator, inverting terminal input will compare and provide the output, and there will be a ending up clock pulse and change in output again will be given to the counter, and it will change the bit position. This process will be continued till the end of conversion. So this is a counter type ADC. It counts the particular pulses. Counter type ADC, which we have seen, initially the counter is cleared, then the analog signal is applied to the one of the input of the comparator, as I have already told you. Counter output is converted into analog by the DAC. The DAC output is compared with the incoming signal, and conversion stops when digital output is greater than incoming signal. This is the procedure of counter type ADC. Then we will go the successive approximation ADC. Successive approximation type analog to digital converter. This is the diagram for this successive approximation type ADC. You can see here, this is the comparator where the analog input is given. Analog sample is written here, that is analog input is given, and the inverting terminal of the comparator is connected to the DAC, digital to analog converter. The output is given to the control logic, and control logic output is given to the SAR, that is successive approximation registers. Here registers are there for each bit, LSB and MSB is there, and this is a programmable center, and the clock pulse is applied to this SAR. And if there is change in bit position, DAC will observe it, and again it will given to the comparator. It will compare with the analog input, and this comparator output again given to the control logic. Control logic output is given to the SAR, and SAR will change according to the bit position. Successively it will happen, approximated bit by bit successively, and it will provide the output, analog output, analog to digital output. SAR ADC, successive approximation ADC, is widely used type ADC, similar to counter type ADC, except that SAR is used, that is successive approximation registers are used. SAR acts as a programmable up-down counter. This register which we have seen in the diagram, registers SAR, acts as a programmable up-down counter. Completion of conversion triggered by a change in the state of the comparator. We have the trigger signal there, so we can change the bit position, or we can make the completion of the conversion also. Much faster than the counter type ADC. This SAR ADC is much faster than the counter type ADC. So once again I will go, because this is in your syllabus. You can just see successive approximation register. This one, this is the block diagram of the successive. You just go through the block diagram, draw it properly. It has a comparator, it has a control logic, it has a SAR, successive approximation registers, in which LSB to MSB bits are stored. Clock pulse is applied for the reset and counting to the SAR, from which you will get the digital output. This digital output is connected to the D2A converter, and D2A converter will provide the analog output. Again, this analog output will be compared with the analog input, and again it is output of the comparator is applied to the control logic. This process will continue till you apply the reset pulse or till the end of conversion. This will be continuing. This is the SAR ADC, widely used, similar to counter type ADC except that SAR is used. SAR acts as a programmable up-down counter. Completion of conversion triggered by a change in the state of the comparator and much faster than the counter type. These are the important points with the SAR. The next type of ADC is the flash type ADC. You can see this is the diagram for the flash type ADC. Simultaneous comparison. Here comparators are used. These are all comparators. This is C0, C1, C2, C3, C4, C5, C6. That means 7 comparators are used for the 3-bit. If 4 bits are there, we can use the 15 comparators. 2 to the power 3 minus 1. 1, 2, 3, 4, 5, 6, 7. So 2 to the power 3 is 8. 8 minus 1. 7 comparators are used. 2 to the power 4, 16 minus 1, 15 comparators are used. So for 4-bit output, 4-bit digital output, we use the 15 comparators. For 3-bit output, we will use the 7 comparators. And here you can see each comparator having the 2 inputs. One input is connected with the reference voltage and the another input is connected to the analog voltage, which is to be converted into digital. And each comparator, just you can see here, this C0 comparator is connected through this R by 2 to this point. C1 comparator input is connected to this R by 2 R to this point. Similarly, C2 is connected to R by 2 R and R this point. So this type voltage divider arrangement is there. Last resistance is 3R by 2 and the first ground resistance here R by 2 and all other resistances R. So you can have the value here 0.5, 1.5, 2.5, 3.5, 4.5, 5.5, 6.5. Other will be connected to this analog voltage. So what will happen? The analog voltage continuously will be compared with these resistances or with these reference voltages available at that comparator, and particular comparator output will change. Suppose we have a 100 output. 100 means 100 means 4 to 1 4. 100 means equivalent to 4. So there may be a change in the output of the 4th comparator and other output may be a 0. So the equivalent output, digital output will be here. Similarly, for the 8 combinations of 8 values, the output will be provided by the comparator and accordingly you will get the digital output. Suppose comparator 3 output is high, that will provide a 0 1 1 0 1 1. So that will be equal to 3. So this is called as flash type ADC. Only the particular comparator will flash the output high and that will provide the equivalent digital output in 3 bits. So this is the success. This is the flash type ADC. Why it is called as flash? Because number of comparators are used here. According to the change of the output state of the comparator, the digital output will be provided into equivalent bits. It may be a 3-bit, it may be a 4-bit. 3-bit comparator requires the 3-bit output requires the 7 comparators. 4-bit output requires the 15 comparators. And these resistances are required for the comparison purpose at the comparator, voltage divider resistances. So this circuit you can use for the flash type ADC. Then this flash ADC have For n bit digital word, 2 to the power n minus 1 comparators are required, as I have already told you. Number 1. Number 2. The analog sample is simultaneously applied to one input of all the comparators. The analog sample is simultaneously applied to one of all the comparators. Analog input is same for all the comparator, and this analog input is compared with the another input, that is reference input, which is divided by the resistances. Other input to the comparator is a DC voltage derived from the pot divider network, which we have already seen, R by 2, R, 3, R by 2, etc. Quantization errors. In analog to digital converter, there may be a quantization characteristics, quantization errors obtained. What is this quantization error? You can see here. If we require 1 by 16, we will consider this point, but just above to this 1 by 16, just above to the 1 by 16, a quantization is required here. This will be quantized at this particular level. This will be quantized at this particular level. So this quantization takes place between the certain nearby values to a particular value. Suppose I am saying that I am having a value of 2, and 2 in the step of supposed to be a 1 by 16. Then from 1 by 16 to half part, the value will take 1 by 16. And from 1 by 16 to upper half part, the value will be taken by 2 by 16. Suppose I am having in simple language, value is 4 to 5. From 3.5, it is above the 3.5, it is quantized to 4. And below 3.5, it is quantized to 3. In similar way, this quantization takes place, and quantization error may occur in the A to D converter, that is to be care. So this is all about the D to A and A to D converter. So dear students, I request you kindly go through the books for D to A and A to D converter, or you can ask me for the notes also if you require. You can observe this video very carefully, and you have any doubts on D to A converter and A to D converter, two types of D to A converter and two types of A to D converter you have to study as per your syllabus. In your syllabus, two types of A to D converters and two types of D to A converters are there. But I have shown mostly all the types of D to A converter and A to D converter in this video. So dear students, kindly go the details of this A to D and D to A converter, and if you have any doubts, you can ask me at any time on any platform, please. In next video, we will go for the certain another part called as a part of the instrumentation. So we will go to the basic idea of the instrumentation in the next video, because your syllabus has the last part of the instrumentation, generalized instrumentation system, then measurement of temperature, measurement of pressure, measurement of velocity, etc. of the instrumentation system. That we will go one by one in the videos of the instrumentation system. This is very important part, and the remaining will be the digital. Some digital part in your syllabus is also there, that we will see also. And later on we will go for the practicals. I have already given you to write one practical. I will provide you the second practical to write in your practical file. And later on I will explain all the practicals. Thank you very much for listening this video. Thank you all.